I welcome all of you to my lecture series on structural analysis with the finite element method. This will be a consolidation series in the finite element method, particularly for the structural analysis. In this consolidation series, we'll be talking about the mathematical concepts of solving the structural analysis problems using the finite element method. We'll be starting with the one-dimensional finite element cases, the bar elements, then the beam elements, then the trusses, and the theory of plates and shells will also be revisited and resolved with the help of the finite element method. Apart from the mathematical concepts that we'll be deriving or we'll be solving, we will also go through the fundamental MATLAB programming for the structural analysis problems. Um, let's begin this course or the lecture series, and we will be starting our entire series from the fundamental concepts, and we'll begin with the 1D finite element for actually loaded rods. 1D finite element for actually loaded rods. So this will be the basic concepts from where we'll be actually understanding how we use this finite element method for solving the structural analysis problems. Before we understand the concepts of finite element methods, let's revisit a very important concept or a very important principle that we have to use in fact in our every topic. Yeah, I'm talking about the concept of the principle of virtual work that we have to use very often. The principle of virtual work. Okay, so as far as the principle of virtual work is concerned, let's talk about any body which is an elastic body subjected to the body forces. Okay, subjected to body forces like Bi, and we know body forces are expressed per unit volume, subjected to the surface traction forces, which we express in the form of T, traction forces. And we know these body forces and these traction forces create internal forces, internal reaction forces in the body, as a consequence of which the stresses are generated in the body. And when we write the principle of virtual work for any elastically deformable body, we write it first of all the virtual work done by the body forces, that is Bi, the virtual displacement, that is del ui dv, because body force are expressed per unit volume, so we'll be writing it in the form of a volume integral, plus the work done by the traction forces, which are expressed per unit area, so that will be Ti, which is a function of x, and the virtual displacement, that is del u and ds. Okay, this is the work done by the external forces will be equal to the virtual work done by the internal forces, and the internal forces are the forces which are created by the stress, what we write as tau ij multiplied by the virtual strain del ej, and this will be the virtual work done per unit volume, so it will be dv. So this is what we actually call as the principle of virtual work when we apply it for when we apply it for the linearly elastic body. If we look at the left hand side of this principle, this is the virtual work done by the external forces. This is the virtual work done by the external forces, and if we look at this expression, this is the virtual work done by the internal forces. This is virtual work done by the internal forces. Okay, So the virtual work done by the internal forces has to be equal to the virtual work done by the external forces, and that is what we call as the principle of virtual work. Now, let's take into consideration an elastically deformable body. Since we have to start with an actually loaded rod, so let's start with the rod element, or let's start with the rods. Let's suppose we are having a rod and its length is, say, for example, L. This rod is prismatic, okay, since due to the lack of control over my writing board, I'm making some mistakes, but you should take it that the rod is absolutely prismatic. Okay, let's suppose this is a prismatic rod, and this prismatic rod is subjected to, say, for example, force at point 1. This is force Fx1. This is force acting along x-axis at point 1, Fx1. Let's suppose here is also force acting along x-axis at point 2. Let's call that as Fx2. Okay, this is force at point 2. Apart from these point forces, let's suppose that this rod is also subjected to the tractions, which are the forces per unit length. Okay, so there are tractions to which the body is subjected, and we write traction small t, it's a function of x. There's no body force, no gravitational weight being taken into consideration. This traction and this external point force will create the stresses in the body, and we are asked to write the principle of virtual work for this case. Let's recall the statement for the principle of virtual work states that the work done by the external deforming forces. Let's suppose that the body undergoes the virtual displacement, that is delta U. Fine. Therefore, the work done by, let me write the work done by the traction. Okay. Since traction is T of x, okay, multiplied by del U, okay, and d of x. Why d of x? Because this traction is a force per unit length, okay. So this will give us the force, the traction force multiplied by the virtual displacement will be the virtual work done by the traction force. So what will be the total traction? We'll write that as integral from 0 to L, okay. Plus, what will be the virtual work done by the force Fx1, that is Fx1 multiplied by delta U plus Fx2 multiplied by delta U. So let's write this as summation of I going from 1 to 2. We can write this as Fxi delta Ui. Okay. This is the work done by, this the virtual work done by the external force has to be equal to the work done by the internal forces. That is the stresses sigma, and let's suppose the virtual strain is delta E and dV. This is the virtual work done by the internal forces. This statement can further be, we can modify this as this. We can write as sigma multiplied by the virtual strain multiplied by dV, that is dA into dx. Now, as far as sigma into dA is concerned, that is equal to the force, the normal force acting at the cross section, force acting at the cross section multiplied by the virtual strain d of x. Therefore, the total work done will be a single integral 0 to L. Okay, this will be the total virtual work done by the what we call as the total virtual work done by the internal forces. So this is how we write the principle of virtual work for this case. Writing the principle of virtual work statement will be our step number 1 in solving the finite element problems, in solving the structural problems using the finite element method. And this should be, realized come what may, that as students of finite element, particularly when we are making use of the structural analysis, finite element for structural analysis problems, it's very important that we know how to write the principle of virtual work for these types of problems. Okay. Now, after realizing and just brushing up the principle of virtual work, let's start our let's simply start our lecture. Okay, so we are talking about one-dimensional, 1D finite element analysis of rod. Okay, and the rod is very special. We will be calling it as an actually loaded rod. Okay, so this is 1D finite element analysis of an actually loaded rod. So we have in the back of our mind that whatever be the problem given to us, we should be knowing how to write the what you call as the work principle of virtual work for the given problem. Okay, though we can solve the problem using the Galerkin's method, using the Rayleigh-Ritz method, using the principle of the minimum potential energy, but it is somehow recommended, as long as you're in the structural analysis, we should be knowing how to write what's known as the principle of virtual work. Now, let us assume that we have a prismatic rod and we assume that this prismatic rod is of length L. Okay, this rod is at this end subjected to a force P. Okay, now the question says, how much is the stress in the rod at different points? How does the stress vary inside the rod? What about the strain in the rod? As you move across the length of this rod, how the strain varies. Okay, how the deformation in the rod U varies. This also we have to talk about it. And we have to talk about normal reaction that is generated over here. Let me call that as R. I'm not concerned about the direction of the R, because I know while I write the equations of equilibrium, the direction of the R will be set right. So calculating this R is also one of the questions out there. So this is a problem in front of us, and this problem is to be solved, but we have to make use of the finite element formulation. Well, I will be doing this. I will be solving this problem using two steps. Because I have started this lecture first with the principle of virtual work, I have to make you understand or make you realize why we have to write, first of all, the virtual work statement of the given problem. Apart from, okay, so that's very important. Why we should know. So that's one important thing. Okay, so before I hope that will be my part two of solving this question. Okay, so let me solve this question using the finite element formulation. Okay, so apart from this load P, let us also assume that this rod is subjected to surface tractions. Okay, and the traction T is a function of X. Okay, the step number one in finite element formulation is often stated as dividing the problem into elements, into finite elements. Divide this problem into finite elements, small elements. But I believe this is not the step number one in finite element formulation. I believe that step number one for any finite element formulation to take place is, first of all, either the Galerkin statement or the Rayleigh-Ritz statement or principle of virtual work or the principle of minimum potential energy. That should be written somehow. Okay. Okay, now let us first of all divide this problem into divide this problem into finite elements. We can divide it into numerous elements. Okay, many n elements, that's our choice, how many elements we divide. So since this is our problem one, let us suppose that we are dividing this entire rod into two elements, and this we consider as a single element one. So this element is having two ends, end one and end two, and these ends we specifically call as nodes. So this is node. Okay, so this is a single element two noded problem. Now on every node here, we may be having some degrees of freedom. Okay, so we may be having 1 degree of freedom to, we'll realize and understand it as we will go ahead. So we have divided this rod into a single element. Okay, now after dividing this rod into a single element, we will also realize that this rod is now, we assume the step number 2 is assuming the displacement inside the element. Let's assume the displacement inside the element to be u as a function of x. And let's assume that u as a function of x is a linear function of x. It's equal to alpha naught plus alpha 1 x. Okay, this is our x-axis. So why we have selected this to be a linear function of x? That's the question. So that's some question out here. We will be certainly answering these questions as we will go ahead. Okay. So since we are talking about stress is equal Young's modulus times strain, that is written as E into du by dx. So if we can calculate this u, we can calculate strain. If we calculate strain, we can calculate stress. So once we calculate stress, multiplying stress with area, we can calculate this P or this normal reaction. So we are mainly interested in understanding the value of this U. Okay. Now, so we write U. This U displacement should have specific values at node 1, at node 2. So we write at node 1, U1 for element 1, U should be equal U1, and that will be, we'll call this as x is equal to x1. This is our x is equal x2. Fine. So u at node 2 for element 1 has to be equal to u2 at x is equal to x2, and this is at x is equal to x1. Fine. Now as we go ahead and write this equation in terms of u1 and u2, we'll write u1 is equal alpha naught plus alpha 1 x1, and u2 is equal alpha naught plus alpha 1 x2. So from this equation, let's calculate the value of alpha naught and alpha 1 from these two equations. As we solve these two equations, we obtain the value of alpha naught is equal, alpha naught will be equal x1 minus x2 divided by u2 minus u1. Okay, that is alpha naught is equal u1 minus u2 divided by x1 minus x2, and this is for element 1. You can put a superscript over it, and we should develop a habit of writing this superscript for element 1, because as we'll go to a number of elements, we have to put these superscripts. And as far as this alpha 1 is concerned, let me write that over here or here. Alpha 1 is equal x2 u1 minus x1 u2 divided by x2 into x1, and that is for element 1. Okay, this is for element 1. Since we have a single element over here, we have to put this superscript. Now let's write this. So we know the value of alpha naught and alpha 1. Let's write this u as a function of x in terms of this alpha naught and alpha 1. So we'll write u as a function of x, okay, is equal u1 for element 1 minus u2 for element 1 divided by x1 minus x2 plus x2 for element 1 u1 minus x1 u2 for element 1 divided by x1 x2 for element 1 multiplied by this entire term multiplied by x. So let's get these u1 terms on one side. You will write u as a function of x is equal u as a function of x is equal x2 minus x for element 1 certainly, divided by x2 minus x1, x1 for element 1 and u1 for element 1 plus x minus x1 for element 1 divided by x2 minus x1 for element 1 by u2 for element 1. Okay, this term is written as, we can also write this as n1 as a function of x, u1 for element 1. This we also write as n1 for 1 plus this term we write as n2, since it's also a function of x, n2 function of x for element 1 multiplied by u2 of element 1. This is u of x. So we have written this displacement in terms of n1 and n2. Okay, so if we look at these n1 and n2, so first of all, see n1. Let me suppose this is our x-axis, and let's suppose that this is our y-axis, or this is n. This is ni. We are plotting on this side. I goes from 1 to 2. So if we look at this n1, at x is equal to x1, this becomes x2 minus x1, x2 minus x1. So ni at x is equal to x1 is equal to 1. Okay, and at x is equal to x2, this becomes 0. So this is x2, this is x is equal to x2, this point. So here our ni is 0. Here our n1 is equal to 1. Here our n1 is equal to 0. Since this is a function of x, linear function of x, so it means as we go from x1 to x2, the function of n1 is like this. This is how n1 behaves as we go from x1 to x2. Now see, if we talk about now x2, n2, okay, our n2 is equal, at x is equal to x1, at x is equal to x1, our n2 is equal to 0. So x is equal to x1, our n2 is equal to 0. So here n2 is equal to 0. And if you look at x is equal to x2, when this is x2, so this becomes equal to 1. Okay, so the function is like this. So this is how n2 is behaving. So if you look at any point, if you take the summation of n1 plus n2, that will come out equal to 1. And you know, these n1 and n2, they are called as shape functions. So they are called as shape functions. Fine. The summation of these shape functions is equal what you call as 1. Now, if you look at this ni has two values. Ni is equal to 0, ni is equal to 1. Okay, and ni is equal to 0 when I is equal to 1. Okay, so or I can say ni for two nodes, I can be 1 or I can be 2. So if you have n1, this n1 at I equal to 1 is 0. Oh, sorry, this is equal to 1. And this n1 at I equal to 2 is equal to 0. Fine. So this is how this ni actually behaves. This ni takes two values. It's either equal to 0 or it's either equal to 1. Okay. So can I express this ni in this form? Ni can be written as del ij, and that is having values. When I is equal to j, it's having value 1. When I is not equal to j, its value is 0. So certainly we can express the shape function ni in terms of del ij, which is known as the Kronecker delta notation. in terms of the Kronecker delta notation. So let's deal with this Kronecker delta notation later on, but somehow we realize that, and the sum of all these shape functions, Ni has to be equal to 1. N1 plus N2 plus N3 plus so on has to be equal 1. Okay. If you look at the summation of del ij is written as del 1 1 plus del 1 2 plus del 1 3 plus so on. It actually includes 9 components, as we know from solid mechanics, plus del 2 1 plus del 2 2 plus del 2 3 plus del 3 1 plus del 3 2 plus del 3 3. Okay, and that's equal, this is equal to 0, this is equal to 0, this is equal to 0, this is 0, this is 0, this is 1, this is 1, this is 1, that is equal to 3. So if you divide del ij by 3, that's equal to 1. That is what this ni represents. Okay, that's what this shape function, their summation always has to be equal, it has to be always equal, what you call as 1. Okay, we'll come to this, but somehow we should realize over here that the shape functions can be expressed in terms of this Kronecker delta notations. Okay. Okay, so if we write now the shape function, so we are writing u as equal n1 x u1 plus n2 x u2 for element 1. So what will be the strain? That is equal du by dx, and that is equal, what is x n1 equal? X2 minus x divided by L, length of element. Okay, that's d by dx into u1 for element 1 plus d by dx n2, that is x minus x1 divided by L into u2 for element 1. So as you do the derivation, the strain inside this element, that is minus 1 by length of element. So we'll write this as length of element 1, u1 plus 1 by L u2 for element 1. Okay. Now if you look, u1 is constant, u2 is constant, L is constant, therefore strain is also constant. Strain is also constant. So as we are using an interpolation formula, alpha naught plus alpha 1 into x, what we are getting is the constant strain. Now the question is, what will be the stress? Stress is equal Young's modulus times the strain. So if this term is multiplied by the Young's modulus of elasticity, we'll get strain, we'll get stress. Okay, what will be the force? If you have to multiply this by area, we'll get the forces. Okay, so we have obtained the forces, stresses, and strains inside the rod subjected to the tractions, subjected to the what you call as the normal force. We have obtained these stresses, these strains, so on and so forth. This is for a one element. Okay, but somehow we need to modify our finite element approach towards these types of problems. This is not simply how we should jump into the finite elements. Okay, so the procedure of finite element is quite different than the procedure we have just started with, though more or less it is same. So it will be like first of all, the finite element procedure will start with few steps. The step number 1 is writing the principle of virtual work, PVW, writing the principle of virtual work. B, after writing the principle of virtual work, writing the um, the displacement function. writing the displacement function, and substituting the displacement function back into the principle of virtual work to obtain what's known as the equilibrium equations for the element. To obtain the equilibrium equations for the element. To obtain the equilibrium equations for the element. Then we will be assembling those equilibrium equations. Fourth step will be assembly. And fifth step will be applying the boundary conditions. Applying the boundary conditions. Okay. So we will revisit this problem, okay, in a more sophisticated manner. That will be how the finite element actually behaves. We'll be solving this problem, and the problem will certainly be solved with the help of the principle of virtual work and taking finite element into consideration, and that hopefully we'll try to do in the next class. Thank you very much.